Yes, I'm going to talk about a few ideas for incorporating domain knowledge into learned models, in particular domain knowledge in the form of known symmetries of the target problem. So this kind of the topics I want to talk about. Depending on time, I will skip some of them or not. So my motivation is that as you think about applying machine learning to a real-world phenomena, and also just purely think in terms of machine learning, obviously there is a huge amount of domain knowledge in various areas where you might want to apply machine learning. And in particular, in fundamental physics, in particle physics, there's a very nice story in terms of symmetry groups and the symmetries of nature. But you can have things that have more like emerging symmetries, like symmetries of molecules and polymers, etc., or even something much bigger, like symmetries of three-dimensional scenes and three-dimensional objects or fluids. So, this prompted me to think about better ways of incorporating this knowledge into generative models. So first, to give some language and notation. So I assume that we know in advance the symmetries that we have in the data. I know that my data is a rotational invariant, translational invariant, or there's some symmetry group. And then the idea is that we have generative models or neural nets, which are really just functions, from one set A to one set B. And we assume that we know how the symmetry group acts on elements of set A, and now I have these general concepts. Obviously, invariance means that this function does not change, so if you have a probability density that is rotational invariant, it means that if I act on it with an element of the rotation group, it's going to remain the same density, like a spherical Gaussian, for example. This is just putting names to things. So we say that a function is covariant, transforms covariantly when basically it commutes with the action of the group, but with different representation. And we say that's equivariant when it transforms in the same representation as the input. So these are just names and definitions. So I'll be talking about generative models. So when you talk about generative models, you cannot really distinguish between these three pillars, which is, so this is a very similar picture to what you saw in the talk earlier today about using statistical mechanics to understand machine learning. I'll focus on the generative process here, but you have to keep in mind that you cannot really disentangle the learning principle, which is what is the objective function of generative models and how we choose to approximate that learning objective. So I'll focus on the generative process, assuming that the two other things are fixed. So going that direction, I will work on a particular class of models that we call normalizing flows. So the idea of normalizing flows is pretty simple. The idea is that we can start from a very simple probability distribution, let's say a spherical Gaussian, and we can apply a series of diffeomorphisms to the data. And then every time we make it slightly more complex. And obviously, if you transform according to a diffeomorphism, we have a very simple formula that relates the probability density before and after the transformation under a few assumptions, but that's a pretty general formula. And the idea is that you can compose this very easily and build increasingly complex density. So obviously, this idea is very simple. All the creativity of this idea comes in coming up with the family of diffeomorphisms that are expressive enough, that are easy to compose, and that have cheap determinant of the Jacobian computation. So that's all about. Every flow paper is a different creative way of coming up with the structure of these little transformation invertible smooth functions that have cheap computation, that you can cheaply evaluate determinants. So you can use this idea to build densities on all kinds of manifolds. Don't have to work on Rn. So we can do a lot of things with this. One particular case of flows is the flows induced by Hamiltonian dynamics. And this is the thing that I'm going to use for what's next. So Hamiltonian dynamics is in a very, very basic way, without talking about manifolds or anything, non-Euclidean geometry, is defined by dynamics on a state space. This dynamics is described by ODE, induced by a function that we call the Hamiltonian via this formula. And a convenient object to play with different objects in this different quantities in this formulation is this bracket thing, which is called the Poisson bracket. So this is just a particular case of a flow. So I can define now normalizing flow a density by starting with a density at time 0 and then evolving these points according to Hamiltonian dynamics, and this cloud of points that I had in the beginning will define a different density in the end. So I can use that to build a complex density. To expand a bit more, I introduced this definition of this operator T, which is in physics is called a infinitesimal canonical transformation. This will be on object that appear all the time. So this object obviously has some obvious properties. It has constant divergence, which means that this Hamiltonian ODE will be volume preserving in the full state space, which means that once you build these discrete flows out of this canonical sequence of infinitesimal canonical transformations, it will also inherit this property. And obviously, it is invertible, at least in the limit of time going to 0, and in certain circumstances, even in discrete time. So if you write this as in a neural net kind of language, you can write it as a graph like this, where you do a sequence of computations where each transforms the initial density pi into a more complex density. This is just an illustration of the same thing. So if you implement that dynamics, you can learn some interesting things with that. So if you parameterize now your Hamiltonian with a kinetic energy term and the potential energy term, both are neural nets. Now we can fit the final density that you get to some target, and indeed you can learn various kinds of multimodal complicated shapes density there. And we can look at what the kinetic energy term has learned and what the potential energy has learned. And you can indeed see that the potential energy learns something that you would expect from data distributed in this way, is that it learns a bunch of attractors at the modes of the data. So we can do some analysis and interpret this. So basically, we are learning Hamiltonian dynamics from data by creating a model that defines density via Hamiltonian ODEs. So now, how can you use that to incorporate symmetries? So I'll summarize a few mechanisms that have already been considered and that are being used to incorporate domain knowledge. First, the first example is the most popular example is the convnet. So the goal of a convnet is because we know that whether a cat is a cat or a dog is a dog, it doesn't matter where it appears on the image. It doesn't matter the orientation it is on the image, etc. So the convolutional operator is nothing but a group convolution operation. It's convolving over the elements of the translational symmetry group. Of course, it's an approximated symmetry because you're discretizing the image as a grid. And the way of building invariance is by applying a pooling operator on top of a group convolution. That's the most trivial mechanism that we could use to build invariance. So another mechanism is directly to exploit group invariance. So I want to build a neural network or a function that is translational invariant as a function of a collection of vectors. A general way of that is that I know that the distance between points are translation invariant, so I can just build a function that takes distance as input, doesn't take directly the points. So that is a very simple idea, and this is what kind of this pairwise kind of graph net interactions allow us to do very nicely. So of course, in physics, you have more interesting symmetries. So if you have your data lives in a manifold with SUN symmetry, for example, that's how it transforms according to a bunch of conjugation operation. You can build a neural network to be invariant with respect to this gauge symmetry by building a network on top of group invariants. So this is how you build every physical observable in physics is by building functions that are themselves functions of group invariants. So this is one example. So just to summarize and put a bit more language, just to recap. So we have this canonical transformation operator or generator with, in the context of this operator, we say that F is a generator because it generates this transformation. And in the Hamiltonian language, we can define a symmetry or a symmetry generator as a function that commutes with the Hamiltonian. So if your density is described by Hamiltonian dynamics, and you want that density to be invariant with respect to a group of transformations, this will play a fundamental role. Basically, it gives this a necessary condition for the density that you get from the Hamiltonian dynamics to be invariant. And these are just some observations. If you could collect the set of all symmetry generators, they form what's called a Lie group, and they are closed under the Poisson bracket. So if you take two symmetry generators, compute the Poisson bracket, you get another symmetry generators. And these facts play a role in how we can build these Hamiltonians. So this is a very short paper that we wrote investigating this direction. We can put these things together in a very simple result, which is that if I have a collection of such functions G that express the infinitesimal symmetries of my problem, I can just translate another theorem to machine learning by saying that if I can build a normalizing flow from the Hamiltonian dynamics such that this property is valid, and I start from an initial density that itself is invariant, like what is expressed by this equality, these two things are sufficient conditions for me to build a density that itself is invariant. So one other way that you could incorporate that doesn't require specifying exactly this functional form of the Hamiltonian, which is to just impose the symmetries to an arbitrary, to keep the Hamiltonian function as arbitrary as possible, but enforce the symmetries via Lagrange, via augmented Lagrangian method. So this is the direction that we explored in this particular paper. We are exploring various other directions in incorporating the symmetries on H directly, which in some cases we can show that's more efficient. So this is just a toy example to demonstrate the gains of this. Imagine you have a probability density that has a circular symmetry, so I can say that it has SO2 symmetry, and this is the generator of two-dimensional rotations. And now this could very well be describing angle distribution in some molecule. And the idea is that what we show here in this little experiment is that you have available an infinite amount of data. It obviously makes no difference whatsoever whether it imposes symmetry or not. The model eventually learns from the data to have the right symmetry. And then you don't see any difference between train and test data in this regime. But in the regime of very, very scarce data, we have a very small number of data points. All the models, whether they have symmetry or not, they think they're doing very well in that data. But what they are effectively doing is learning a bunch of deltas around the data points that are available. And when you look at the test set, the models without any knowledge of symmetry whatsoever, they just massively overfit to the problem. But we can pretty much control the degree of overfitting by how hard we impose the symmetry constraint that we know exist in this problem. And this is an example of the learned function under the symmetry that has a very fine granular precision on this learned symmetry. So this was a very small example that we are trying to extend and generalize now to more useful domains. So another question that also motivated this work is, can you learn symmetry from data? So if I look at data set, can I say something about the process that generated this data? Can I say something about what kind of symmetry it might have? So this is a very hard problem, and this is one problem that we try to investigate. So one of the first things we could imagine is that, of course, if we introduce a basis function where we can express both the Hamiltonian and the generators, of course, once you introduce this basic function, you know, we'll define the Hilbert space, etc., everything becomes a linear algebra problem. And you can rewrite the problem of finding the symmetry generators, which are these coefficients, as a problem of finding the kernel of a matrix. And that was one of the first things we did in this direction of trying to extract the symmetry from data. To test that, we created a very simple physical system, let's say a mass spring. We know exactly the symmetry generators there. They are the rigid translation and rotation around the center of mass of the system. And now, since we have reduced the problem of finding, so basically this is the final problem. We have this matrix M, which is just a function of the structure coefficients of the basis and the coefficients of the Hamiltonian in that basis. And the problem is to find the left null space of that matrix. That's what we reduce the problem to. And this is what we're looking here. So if you do a singular value decomposition of this matrix M, we can now sort the singular values, and we can look at what is the dimension of the null space as a function of this relative condition number, which is just a threshold on a singular value. At which point I consider singular value to be actually 0 or not. At which point I consider something to be a symmetry or not. When you look at data, you have to make this threshold somewhere, and this is what it is looking here. So in this very simple physical system, you see that as we grow the threshold on the relative condition number, there are some hops in the dimension of the null space of that matrix, and these hops correspond to the discovery of some symmetry generators of the system. Of course, if we include all the singular vector, all the eigenvectors of that matrix, we just recover the whole space. We're not talking about the generators anymore. And now, in this very simple physical system, it's relatively easy to identify the generators by looking this way. And here we can also see how it appears in terms of the reconstruction error of these generators as a function of relative condition number. So since this is about, as we grow the relative number, we are growing the size of the null space until it goes from empty set to the full set. Once we hit the dimensionality of the smallest set of generators of symmetry, we should see massive drops in reconstruction error of the symmetry generators, and that's what we see here. So I have these 3 generators, their error just fall to 0, whereas these are other examples of functions that are not symmetry generators. So things that are not symmetry generators, I may need the full space or a much bigger set space there. So this is one tiny step towards trying to find this one. This is a different physical system. I forgot which one that's not the mass spring. But the thing is, to do all this computation, the choice of a basis obviously is very important. And I would say that by far, we don't have a robust way of doing that yet. But that's one step in that direction. So we tried to, not satisfied with this, we tried to do something even harder, which is these systems, we are trying to express a known Hamiltonians in a basis and then rediscover, pretending that you don't know the symmetry generators by looking at how the Hamiltonians projected there. But what if I just have a bunch of data? How I can extract symmetries there? So what we tried here, which you might see mathematically outrageous, is just we refit the Hamiltonian to that data. That's what we have, a bunch of physical systems with very simple Hamiltonians. And this is just to show that it learns to simulate that to a very reasonable accuracy. So we can extract Hamiltonians from data. And then we can use an optimization algorithm that finds non-trivial functions that commute with this learned Hamiltonian. And this is kind of things it learned. And then we apply these functions that we found that are supposed to be symmetry generators. We apply a sequence of canonical transformations with these symmetry generators to the state space to see what happens. So this is an example of what it learns. Basically, it learns to apply a bunch of translations and create and remove balls. We found very tricky to disentangle this space. It finds basically these arbitrary functions, which are arbitrary combinations of the generator. So it's going to do a rotation followed by translation and followed by a bunch of nonlinear combination of these things. So it's very hard to extract clean symmetry generators with this idea. So this is what I would like to present at this time.
Thank you very much, Danilo, for this fascinating work. We have time for questions. Yes, Shirley?
Just Danilo, quick question. So if you had generators of only 3 balls, say, would you still generate things that have more than 3 balls bouncing around? It seems like it, but I'm not sure.
You mean the symmetry generators? Well, it depends on how you express it. So if the neural network that represents the symmetry is itself a graph net-like thing that can take an arbitrary number of inputs, maybe. But here they are like fixed size. So once they learned to approximate a subset of the algebra of generators, then that's frozen. But you could imagine how that would be able to be extended. Yeah.
Other questions? Yes.
In your example with the Hamiltonian and again the 3 balls, the learned Hamiltonian, does this have some like kind of parametric form, or is it some horribly complicated function? So we know the physical one, so I'm just curious about the comparison.
Yeah, so we did various imputation experiments. For example, we know that the real Hamiltonian, its form, so we could relax some of the terms, for example, relearn the masses, for example. That worked very well, but in these particular examples, we put no constraint whatsoever on the functional form. It's just MLP, fully connected, that takes the state space and outputs an energy. And the only structure we had here was that the Hamiltonian was factored into kinetic and potential energy, but that's for the reasons of having a symplectic integrator that's easily accessible. Yeah.
Any other questions? If not, so if you take this now and go back to like particle physical cosmology, is this, would you say this is a way also to add domain knowledge and combine modeling with learning?
Yes, that's partially what I mean by adding more domain knowledge to machine learning. I don't mean completely replace machine learning by the non-Hamiltonian, but relax a little bit in a way that respects the non-symmetry. So if I'm learning a model that does a fluid simulation, for example, I don't want this model to learn to conserve mass or to conserve energy and momentum. Right. So I want them to, whatever it learns, to exactly respect this knowledge, for example. And this is the direction I think we are going with this. Yeah.
Sure. So based on your last comment, so how do you contrast that with, we now have a lot of methods for basically auto-differentiating simulators, which is basically exactly our domain knowledge. So how do you contrast this idea of having a Hamiltonian flow with, for instance, having a layer in a neural network that can just evaluate and flow the Hamiltonian forward? You could give it some data, have a differentiable simulator, and then continue processing after that. How would these things?
I think that's great. So if you have the differentiable simulator with the known parts, then it's probably better to use that. Although, as we've seen as well, it may not be, once you consider the bigger picture of the optimization and the approximation involved in optimization, it may not work as well as having more learnable modules inside. We've seen this in, there's a very active area of research in the computer vision community of building a differentiable ray tracer programs. A ray tracer is basically a light simulator. It simulates light bouncing in objects. And although you can build ray tracers that are differentiable, the gradients of, and even if you look at up to second order, they are horrible. You have these very flat landscapes, and the near objects, they are very large norms, gradients, etc. So you may face similar issues there if you have a model that was just given to you and you try to optimize it. But if that works, I think that's also a great way of combining knowledge, and then maybe combining that with other ways of optimizing just a small number of parameters that, you know, maybe initial condition or some unknown coefficients, something like that. I think that's it's complementary, yeah.
Okay, let's thank Danilo again.